Okay, so the third lecture is about one particle states. This is section 2.5 of Weinberg. And herein we will define what a particle is, in at least in the context of quantum field theories. So when you imagine a particle, we usually imagine this sort of little sphere, which we know is not a sphere, it's a point particle, but at the same time it's quantum mechanical. So we also sort of fuzzy imagine this fuzzy extended wavy object. It is a wave, it has some wave vector, and this wave vector is also fuzzy. So this sort of mess we imagine, I mean, at least I imagine this. But here we will try to look at it from a different point of view. We are not going to look at a particle from a classical picture. That we will not assume that the world is a classical picture and then we are going down to the quantum level and trying to figure out what a particle is. No, that we are not going to do that. Instead of that, we will define a particle from a symmetry point of view, that our universe follows these symmetries, and whatever transforms in a certain way under these symmetries is what we call a particle. So if a particle on the classical side could be whatever, it can have any picture, but we know on the Hilbert space side it is described by some state psi. And if this state psi under our symmetry transformations, in particular under Poincare transformations, which are described by lambda unitary transformations, which are dependent on these Lorentz transformations and space-time translations. So these unitary transformations act on this state psi, and if these states preserve, if these transformed states preserve the probability amplitude, as in if let's say psi phi is this sort of a amplitude under the transformation u psi, and this becomes, let's say, u phi, and these are the same as the previous one, then we call it a symmetry transformation. And whatever states that transform under this symmetry transformation, we can call them particle states. Now, in particular, what is a one particle state? We will try to answer that. So first we can start with this. We will start with the Poincare symmetry, that our universe in flat space has Poincare symmetry, which consists of Lorentz transformations, which itself has 3 rotations, 3 boosts, and 4 space-time translations, 3 in space and 1 in time. So these are 3 rotations generated by angular momenta. These are 3 boosts generated by these k's that do not commute. And the 4 space-time translations from these 3 are the momentum translations, and 1 is a time translation, which is the Hamiltonian. So these are the 10 generators of the Poincare group, and they describe a symmetry. And our goal is to see how states transform under these symmetries. So first of all, what we can say immediately is that since P is a generator of momentum, and also we know that these 4 energy momentum vector, they commute with each other. So therefore we can, since this is true, therefore it is natural to label the states of the Hilbert state with the eigenstates of these operators. So in particular, this in particular p square, which is p mu is what called a Casimir. I think it's called a Casimir of the group, which commutes with all the other operators. So since whenever 2 operators commute, they share the same set of eigenvectors. So we can use those eigenvectors and eigenvalues to sort of label our state vectors, the basis vectors, and correspondingly their eigenvalues. The point is, we can define momentum states P, such as when P mu act on them, we get some eigenvalue p mu on this. So we are using these states as the eigenstates of the p mu operator as the states that we are going to use as the basis of the Hilbert space. Once again, this is a continuum. So for instance, a particle moving with some momentum p and with some rest mass, some energy E, not rest mass, energy E, would correspond to, in Hilbert space, a particular state P. So this is a particle which is moving with some momentum P. And this is my Hilbert space. And this is since these are continuous states, let's say a particle which is moving with some other momentum, let's say 2p, would correspond to some other state which is orthogonal to the original one, and all the other states that are in between as well. For example, another one which is at 1.5p would be another orthogonal state, and another one which might be this one will be another orthogonal state, and the whole continuum, any vector in this real physical world would correspond to a particular eigenvector on the Hilbert space, which is perpendicular to all the other previous eigenvectors. So it is not only it's a Hilbert space, but also their basis vectors are all orthogonal, yet they are uncountably infinite. So this is a picture which is a little hard to wrap your head around. But one way is this, that if you want to, let's say, imagine a 3D space, instead of imagining it in 3 space, you can imagine it on a 2D sheet. Imagine you are looking at it, this 3D space, from the point of view of this 1, 1, 1 vector. So on the 3D sheet, you will see something like that, because you are looking at it from the diagonal. This is z-axis, x-axis, y-axis. These angles are all 120 degrees. So you just need a 2-dimensional sheet of paper. Looking from this certain angle, you can see this 3D space. Similarly, it's hard to imagine a 4-dimensional space, but from this same idea, on a 2D sheet, you can imagine 4 axes, x, y, z, and another axis, w axis. And you are looking at, again, from this 1, 1, 1, 1 diagonal. So you can imagine that it will look a bit like that. And then you can continue the process. You can look at, let's say, ND space, from, again, this 1, 1, 1, 1, so on. These n ones are there. So this would again look like, from a 2D perspective, like n-sided pentagon or something like that. Not a pentagon, n-sided, what is it called, n-gon, with this angle being, I think, 2 pi by n. So that's one way to see how these discrete dimensional vectors, finite dimensional discrete spaces look from a point of view of a 2-dimensional, from point of view of this 1, 1, 1, 1 diagonal. So continuing this crazy and sort of hand wavy process, you can imagine a discretely labeled infinite dimensional vector space as some sort of, again, from this 2D sheet, some sort of this ray, and all of these. And by the way, all of these are at 90 degrees. From this perspective, the angles are 120 and so on, but actually these are all orthogonal. In this picture as well, all of these are orthogonal, and similarly these will also be orthogonal. And the difference in this uncountably continuum would be that this whole thing would be filled with so here each vector has some gap within them, and you can label them discretely. This is 1, 2, 3, 4. Even though these are infinite, you can still label them, In the uncountable one, you won't be able to label them. It will be a continuous ring, just like you cannot even start counting on a real number line. After 0, you don't know what comes. I mean 0.0000, and you can move on. You can go on forever, and you won't be able to put a 1 at the end. So this is an uncountable infinity. This is a uncountable infinity. Okay. So this was about sort of visualizing this whole thing. So I can imagine this Hilbert space. This is my infinite dimensional Hilbert space, and its eigenvectors, these p vectors, are there is one vector, there is another vector, there is another vector, and all these lie on this uncountably infinite ring, and so on. You can imagine a ring like that. I'm making discrete countable lines, but you should imagine a continuum of these. So you can imagine that as your p Hilbert space, let's say. And other than that, there is also a possibility that these wave functions or these state vectors come with some other labels, which we are calling sigma. Sigma can be any other degrees of freedom, and these are assumed to be discrete. That sigma comes in a discrete label, not an uncountably infinite label like this p. So this is an assumption which we can justify later on, but for now we will assume that sigma, which label all the other degrees of freedom, this is coming in a discrete, not a discrete. I mean yes, discrete, but countably infinite labels. Well, so the Hilbert space of that thing would be finite dimensional, albeit it will again have many vectors, basis vectors, and the total Hilbert space would be the cross the tensor product of the two Hilbert spaces. So you can imagine your one Hilbert space is here and the other sigma Hilbert space is there, then your tensor product of both of these. What that means is for each direction here, for each p here, there exists this whole space, whole sigma space tensored with that direction. All right. So that's the complete Hilbert space H of the whole state. Okay, so we have this. This is our foundational equation. Then we can show that well, suppose you apply an arbitrary Lorentz transformation on this state p sigma. Well, what would be our expectation? Because a Lorentz transformation lambda will send p, the for momentum p, to lambda p. You can imagine in your real world you had a momentum p, you applied a Lorentz transformation, now your momentum is lambda p. This was your Lorentz transformation. This was done in the real world. So in the Hilbert space, you were first on this continuum ray diagram that I just drew. All of these are rays. First you were on this eigenvector p, and now since in real space the force momentum is lambda p, that would correspond to some other eigenvector that corresponds to lambda p momentum. So on Hilbert space you have shifted from p to lambda p. So this would be some state lambda p and this sigma label. Now we need to talk about what happens to sigma label. Would that change? Well, yes, in principle the sigma part of the Hilbert space can rotate. How can we see that? Well, first of all, we need to prove that we do end up on the lambda p eigenstate. For that, it is easy to show that what happens when this p mu acts on this vector u and p sigma. So this is easy to do. what we can do is just insert an identity right here, an identity of this form, u of lambda, u inverse of lambda, followed by this whole thing, which is p mu u of lambda acting on p sigma, and then we collect these ones. And we know from previous session we found these we found how p mu generator transformed under under this sandwiching of u and u lambda. So it just transformed like a 4 vector. So there would be this lambda mu nu p nu. This was the way it transformed, and we have this acting on p sigma, and then we know that this acts in this way, that since these are states of these are eigen states of p nu operator, so we will have p nu out here, the eigenvalue, and similarly this guy, and then this operator can go through these because these are just numbers acting on p sigma. So what we found is, initially we had this, so what we found is when p mu, the operator p, acts on this state u p sigma, then we get back this state p u acting on p sigma, but with the eigenvalue lambda p, because this thing can be written as lambda p vectors mu component. This can be written as this. So this means just that what I just explained a little bit ago, that if you act the momentum vector on the energy momentum vector on, not the vector, the energy momentum operator on this state, which is u p sigma, you should get a state which has an eigenvalue of lambda p. So that just means this state is such that its its momentum label is of lambda p, and these sigmas we have to talk about. So in general, this sigma, this thing can rotate in the sigma space. That I'll tell you what I mean. Suppose let's start simply. Suppose we have a particle, an electron or something, which is moving in this direction. Let me call this some x, and its spin is in top direction. Let's say it has an up spin, and then we do some Lorentz transformation. Let's do a simple Lorentz transformation, a rotation by some angle theta, so our lambda is just a rotation by an angle of theta, but we will still keep calling it lambda. We will call it lambda. So now in this space, since we rotated, now we have this axis system. This is our particle, this is the spin, it is moving in this direction. So now this is my new x prime direction, this is my y prime direction. Now you can see that the momentum has changed. So the new momentum, this guy, can be written, not the new momentum, the momentum is still in this direction, but from the perspective of these new coordinates, it can be written as some part in x prime plus some part in y prime direction. It can be written as this sum, right? And similarly, if you look at the spin first, if I make the spin state, it was an electron, let's say, so it can have a spin up and a spin down. First it was purely in up state. For example, you could have chosen a certain beam from the Stern-Gerlach experiment or something like that. So first it was in spin up state, so the vector in the Hilbert space. So this is the Hilbert space, this of the spin part. Okay, it's spin. It's the two-dimensional Hilbert space. Actually, it's a C4, but okay, anyway, for the sake of simplicity. First it was in this direction. After a rotation by an angle of theta, it should rotate by an angle of theta by 2. As we know, that the corresponding unitary transformation is e to the power I theta dot sigma by 2. When we rotate by an angle theta, corresponding unitary on the Hilbert space is of this form. So it will rotate by an angle of theta by 2. The point is not about theta or theta by 2. The point is that now the state is not purely an upstate. Sorry, it should have been this, because it was an upstate. I call this axis downstate. Anyway, nothing changes. So this is a purely upstate. Now in the rotated coordinate system, the new state is this, rotated by an angle of theta by 2, or this one, whatever. The point is, it is now mixed. Now the new spin state is it has some component in up spin and some other component on the down spin side. So now it is mixed. What I want to say is that a rotation on the p space also had a effect of mixing the components of the spin state on the spin side of the Hilbert space. You can imagine it in such a way that continuum disk of all the p vectors, this infinite dimensional Hilbert space, this was your HP, and for each one of these there was some Hilbert space. You can imagine some spin state, some sigma space was attached. So for each, and imagine these two directions are perpendicular to this disk. So you can say that for every single p state here, there exists a two-dimensional Hilbert space. For this state, again, there is a two-dimensional Hilbert space, and so on. This is a tensor product. So a rotation in the p space, just like what we did here, a rotation in the p space would throw every eigenvector here to some other eigenvector here. Every p will be thrown to lambda p state on the Hilbert space. But at the same time, this spin section of the Hilbert space can also get mixed. So whatever the state was initially, it can be mixed in the spin part, and it will of course it will mix on the momentum part of the Hilbert space as well. So all in all, what I wanted to say was that this thing that we are talking about, that applying an arbitrary unitary transformation on this p state, this lives in the Hilbert space, this would be, by the way, this is some u lambda. This state can be written as a tensor product, p tensor sigma. So this can be written as p would transform to lambda p, and sigma will transform to some new c sigma. Let's say this c is some matrix, some operator. So in case of spin, this operator was the sigma theta dot sigma by 2, but in general, on any arbitrary degrees of freedom sigma, it can be some operator c. All right, this is what I wanted to say. Or in terms of components, you can also write that u lambda p sigma is just how do I write it? We can write it as follows: sigma prime c sigma prime sigma. These are coefficients, these are functions of whatever Lorentz transformation we did and on what momentum we did that Lorentz transformation on. So this is just a coefficient of this C matrix acting on these lambda p vector and some sigma prime, because these are now the rotated bases, not the rotated one but the transformed bases. So our goal is to figure out these representations that are acting on the other degrees of freedom. We will see that these sigmas are going to be they can be spin or they can be something else, helicity or something like that, but For now, these are just some discrete degrees of freedom other than the momentum eigenspace, momentum eigenstates. Okay. So I hope this much is now clear, that so what we have done here is just that acting any arbitrary Lorentz transformation on an eigenstate which corresponds to momentum p and other degrees of freedom sigma. This will give you another eigenstate with the momentum lambda p, and the sigma degrees of freedom would be transformed in accordance to this new sigma matrix, not the sigma matrix but a matrix C which acts on the sigma part of the Hilbert space, on the sigma sector, not on the p sector. Obviously this is an infinite dimensional Hilbert space, because this infinity comes from this momentum part, because it's uncountably infinite. Sigma space can be finite dimensional, but the full Hilbert space is infinite dimensional, and this unitary transformation is acting on an infinite dimensional state. And there is a theorem that for groups that are not compact, you cannot have finite dimensional representations of that group. What I mean is this. For example, rotation group, the parameters are θ1, θ2, θ3. For rotation group, there are 3 Euler angles. These are compact parameters, as in they run from 0 to 2 pi or 0 to pi or something, but the point is the range is finite. On the other hand, the boost parameter or the rapidity or whatever, they run on an infinite line. You can boost to any arbitrary velocity. So in that sense, the endpoints are not compact. It can be anything from minus c to c, or in terms of rapidity it can be anything from minus infinity to positive infinity. So that is an that is a not non-compact interval. Similarly, the translations are also not compact. You can translate to arbitrary space-time points. So there is a theorem in group theory which says that representations of finite dimensional or representations of compact groups can be unitary, finite dimensional unitary matrices, but the opposite thing, which means that the representations of a non-compact group, and Lorentz group is a non-compact group, they cannot be finite dimensional and unitary. If they are unitary, they have to be infinite dimensional, which is clear from this equation, because of course this is an infinite dimensional representation. So now we would like to do something about this, because instead of dealing with the full infinite dimensional representation, what we would like to do is to study this on a certain subgroup, and then induce the other representations through what we know about that little group. So the idea is as follows. Consider that you have some standard momentum k, and you want to study everything from the point of view of this k momentum, and then later on you can transform to any other momentum p by the help of some Lorentz transformation L of p acting on k. Let me put some indices, mu, k, nu. What I mean is that suppose you have some transformation k in your momentum space, and then you apply a Lorentz transformation L, it brings you to the new vector, the 4 vector p. And from this think of this k as an anchor. This is fixed, this is standard and fixed, and from this you can reach any other momentum you want, any momentum you wish to, just by applying some Lorentz transformation L, which is of course is a function of p, because if you want to reach different p's, you would need to apply a different Lorentz transformation. So this is the main equation that is going to help us from traveling between different momenta from starting from k. Correspondingly, on the Hilbert space side, so this was the physical space, there is some momentum p and then Lorentz transformed version, some momentum k and then another momentum p, which can be reached through this Lorentz transformation L. Similarly, we can posit that there is corresponding to this momentum k, there is a state k with some labels sigma, and if we apply a unitary transformation which correspond to this Lorentz transformation L on this state, this guy, then we can reach this state p of sigma, and this should be taken as the definition, as in if we apply so what we can say that on the Hilbert space, any momentum eigenstate p can be thought of as applying a unitary transformation which correspond to this L Lorentz transformation on the standard momentum eigenvector k. This is the way. And to make it even more general, we can say that there is some constant here, some normalization constant can be present there, which would again be a function of p, because for different to reach different eigenkets in the Hilbert space from this eigenket which correspond to k, we can have different normalization constants. So that's another foundational equation. Here comes the interesting part. What we want to understand is how this guy works. Our goal is to find this, so we can just do that by applying u lambda on p sigma and using the fact that p sigma can be thought of as applying u of L on this k sigma. So I've just substituted the above equation in this one. Alright, now comes the tricky part. What we will do now is we will insert an identity operator here. An identity operator which transforms okay, let me first show it to you. Now I'm going to insert this guy, u L of lambda p and u L inverse of lambda p. This right here is an identity, and let me just copy down these two again, u of lambda, u of L of p on k comma sigma. Let me draw some pictures for you. What I am doing here is this. There is imagine that there is a vector p and there is a vector lambda p. The way to go from p to lambda p is through some Lorentz transformation lambda. All of these are in Hilbert space, and assume that the connection of both of these vectors is through this standard vector k. Now to go from k to p, we will have to apply L of p or u of L of p, because if it's in the physical space we will have to do L. If it's in the Hilbert space we have to do the corresponding unitary operation, but the point is you have to apply L of p. To go from k to lambda p like this, we have to apply L of lambda p, right? And we can think of this vector right here, and by the way, yeah, this one going from p to directly p, from p to lambda p, we applied u like that. What we are doing here is that we are applying first on K we are applying L of P. So we are going from this K to there, followed by U of lambda from there to there. This is our path. Now imagine that we extend our path so that we next go from there to again back here, and then followed by this. That is to say, this equation is just first, once again, if you look at this whole thing, we are starting from K. First we are applying L, so we are going from here to here. This is our first point, this is our second point. Then after that we are applying a lambda, so we are going from 2 to this point, which is 3. Then followed by that we are applying an inverse of lambda P, that is a transformation L, which brings you from which should bring you from K to lambda P, but we are doing its inverse, so we are going from this point lambda P to this point K, so back from 3 to 1, followed by a transformation which brings you from K to lambda P. So this. Now what is the point of this extra identity? So you can see that this one that we did here, this step and third and fourth step, this corresponds to an identity as I written here. This is just an identity since we are going back and forth. But the point is that if you let me say it in this way. What's the point? Yeah, so if you just look at the first 3 steps, that is going from 1 to 2, then going from 2 to 3, and then going from 3 to 4, and then you went from this point to this point again. But wait, let me just label it correctly. Yeah, so we had 1, 2, 2, 3, 3. This should have been 4, which is same as 1, and this should have been 5. Okay, so first we went from 1 to 2, then 2 to 3, then 3 to 4. Now this whole thing is like going from K back to K, and then followed by another transformation lambda P, which brings you to lambda P. So what I can do is write this thing as one block. So this one block would correspond to going from K back to K, which is not an identity. I'll tell you why I'm saying that this is not an identity. Yeah, just I'm writing down the same thing once again, just putting some brackets. U of L inverse lambda P followed by lambda followed by a L, which is a function of P. This whole thing acts on K. Yeah, here I have used this, that U of lambda bar, U of lambda is just U of lambda lambda bar, because these form a group. Okay. Yeah. So I have written the same thing, just that I have grouped these 3, and as you see, the combination, this corresponds to going from K to K, as I explained. You can directly see from here as well. This is K. Then I do a Lorentz transformation which brings K to P, and then this Lorentz transformation brings P to lambda P, and then this is the inverse transformation which again undoes everything, brings lambda P back to K. So this whole unity transformation acting on K should bring K back to K itself. And as you can also see from this picture, this corresponds to this cycle, going from 1 to 2 to 3 to 4, and then the last one going from 4 to 5 is written as this, L of lambda P. So the point of this whole thing was, let me call this thing W. So the point of this whole thing was that followed by U of L of lambda P, U of W, where W is defined as this transformation, and there is this constant that is going on. So the point is that acting W on K gives me back K, or writing it in this form. So this Lorentz transformation W, which is the combination of these 3, right? This Lorentz transformation is defined as this. this transformation brings k back to itself. And there are many transformations that are not identity, but they do that. For instance, let's say you are uh, in a three-dimensional coordinate system, and then you have a vector k which is pointing along the z direction, z cap, and then you do some rotation in the xy plane. So this rotation is not identity, this is a SO2 rotation, but it does not change your z cap. So this SO2 rotation brings z cap to z cap itself, but it is not identity. So you cannot say that W is identity necessarily. Of course, if W is identity, this will be true, but this is true for more non-trivial groups other than identity itself. That's what I wanted to say, right? So this Lorentz transformation, or a group of these Lorentz transformation that leaves this standard k invariant, this is called a little group. And this is the definition of this W as per our thing. And the point is that the corresponding unitary of this W, when it acts on some vector k comma sigma, of course it brings it back to k, but it is possible that this little group would rotate the sigma coordinates, just like that, where we had some c there. We'll use the symbol d here, some sigma prime, some d sigma prime sigma, some over sigma prime, or in particular you can write it as this function of k tensor sigma. You can write it as, this will just stay k, but the sigma can be rotated by some d, like that. You can see that here as well. For instance, if it was a rotation just like here, it was rotation by theta degrees angle along some plane, then it is possible that if your momentum was in z direction and this rotation was happening in xy direction, and your spin was suppose again in xy plane, then it would have been possible that it could be the case that your z, the momentum remains unchanged, but the spin components mix, because spin was originally pointing in xy plane and you did a rotation in xy plane. So this sigma components can mix. This is a possibility. Even though the k is still the same, the sigma components, the sigma side of the Hilbert space can rotate or transform in some way. So this is why what we can do is that we write this guy right here. Yeah, and it was originally just u lambda acting on some arbitrary state p sigma. This thing this whole thing, this is a little group element acting on k sigma. So I will just have this same thing here. I will have a k, but a mixed version of k on the sigma side. And this d sigma sigma prime would depend on some little group W, which in itself a function of some Lorentz transformation and the momentum on which this little group acts on. And then we have k sigma prime. So these are just function labels. What is it? This d is a label of, not a label of, but this d is a function of. And right here we have u L of lambda p, and I have n of p, and then here I have u of lambda acting on p sigma. Now I can bring this one inside, and I will have n of p sigma d sigma prime sigma u of L lambda p acting on k sigma prime. And this, we know what this is, since we know that applying a unitary transformation corresponding to some Lorentz transformation L on this 4 vector k brings it to that momentum eigenvector. I'm talking about this definition right here, or its corresponding definition on the Hilbert space, that applying u of some Lorentz transformation L that depends on p corresponds to bringing k to the momentum p, and this state is just obviously p sigma divided, so I can divide both sides by n, and I can write this much as p sigma by n of p. Similarly here, the p is actually lambda p here, so this whole thing would just be 1 of n of lambda p times this k would just transform into this momentum lambda p, and sigma prime just comes along for the ride, and everything else is the same, n of p. So finally what I can write is that u of lambda p sigma is just n of p over n of lambda p, the ratio of these two coefficients, normalization constants, followed by sigma prime, some d, these are matrix element of the D matrix that acts on the sigma state, acting on lambda p sigma prime, and these are functions of W, which is defined by this. Okay, so once again this result just shows us that if we apply a unitary transformation corresponding to a Lorentz transformation lambda on a momentum eigenket p comma sigma, that would correspond to, first of all, multiplying apart from this coefficient constant factor, that would correspond to this certain mixing of sigma states in the Hilbert space, where the momentum is shifted from p to lambda p, and these d sigma sigma prime, or you can say that this D matrix, which is a function of this omega obviously. Now I haven't shown you that these they actually form a group in themselves. For example, if you have if you had some Lorentz transformation lambda for which the little group was W, another Lorentz transformation for which the little group was W prime or W bar, then if I can prove that the product of these two matrices is just a matrix with the little group W prime W, then I would have shown that these form these D furnish a representation of this group W. So this can be shown easily, it's not a big deal. I can write down the proof quickly. This just follows from its definition, since u of W acting on some k sigma was this sum. It's a function of W. This is some k sigma prime, and then we can apply so we can consider the composite object. We can consider this guy. We can consider this sigma prime T sigma prime sigma, which is a function of W prime W acting on k sigma prime, right? This thing can be in reverse like this, can be written as U W prime W acting on k sigma prime, and then this can be broken up into two parts. Sorry, this bar should not be there. W prime U W acting on k sigma prime. Then we can consider this part alone, then reuse this definition, and then we will get a ket which is proportional to, let's say, some k. Okay, let me just do it. This would just be summation sigma prime D sigma prime sigma W k. Here I'll have sigma prime. I will just use double prime here. K sigma double prime followed by U, and then I can just bring this one inside. Sigma double prime D sigma double prime sigma prime W acting on this ket. We have this guy sigma double prime, and again you reuse this definition once again, this definition. So we'll have sigma double prime d of how do I use it? Okay, yeah, sigma double prime sigma, let's call it, just we can call the label sigma, it's fine, of this acting on k sigma. And then of course, since on both sides we have sigma prime, I can relabel this so that on both sides we have sigma prime, because we started from this. Here I have sigma prime, so I can relabel. In place of sigma I can put sigma prime, and in place of sigma prime I can put sigma. And if everything is right, I can just make it get independent, and I will have this quantity, that summation over sigma prime would be, okay, there should be another summation here, right? Yeah, there should be another summation over here. Sigma prime, this whole thing, d of sigma prime sigma of w, and again I can remove this sigma prime on the outside. Inside I'll have sigma double prime d sigma prime sigma double prime w d sigma double prime sigma w, and again summation, this guy goes away, so I'll just have sigma is just summation over sigma double prime, and this is just what we wanted to prove, because this is nothing but, because this is summing over sigma double prime, this is just the matrix element of this sigma prime, this is just the matrix element of this, of sigma, this is just sigma prime sigma, or you can write it as omega, not omega, w sigma prime sigma. So again, since these are all elements, so we can also say that the whole matrices are such that they follow this rule. And this is just what we wanted to prove, that W's and this D's are the representations of little group. So they, first of all, they form a group. Second, D are the representation of these groups. So from this exercise, what we have shown is that instead of talking about this C, which was such that we didn't know much about the whole unitary transformation and its representations, or either they would not have been unitary, or if they were finite dimensional, or they would have been non-unitary if sorry, that's what I said already. If they were unitary, they would have to be infinite dimensional. But right here, what we are doing is that we are considering the representations of W, which is the little group, which is defined in this way. And we are saying that the way unitary transformations act on the ket is such that these D's act on lambda p kets and summing over them, of course, apart from this normalization constant. So the point is that the problem of determining those C coefficients on top, these ones, we don't have to do that anymore. This problem has been reduced to finding the representations of the little group, and that is actually an easier problem because the little group is easy to find. For example, there are many different cases. There are 6 classes that can be formed. The physically relevant ones are as follows. Suppose you have a massive particle for which m square is greater than 0. For that massive particle, we can choose our standard momentum k, such that the particle is at rest. So when the particle is at rest, it just has its rest mass energy. So the standard momentum is just some mass 0, 0, 0. This is the standard momentum. The point is we can do everything on this standard momentum. And then we can induce our representations by using this formula, by using this relation L of p k nu, or the Hilbert space version of this. So this particle has a little group. Again, little group was a group which leaves this k mu unchanged. Acting W on K should give me back K. So what is the set of Lorentz transformations W that does not change K? Physically, you can see that transformations such as rotations of the 3D space will not give this particle any momentum, because these are just rotations of the space. So that will still keep K of this kind, because again the rest mass energy of the new one would also be m, and the momentum would be 0. On the other hand, if you were to do a boost, then this particle will gain some velocity, and this force momentum will change. So the little group W is nothing but SO3 in case of massive particles. And by the way, there is also a technicality that P naught is also greater than 0 here, the time-like guy. So that's one class. That's one class of solutions. And the next class would be to look at massless particles. Since a massless particle cannot be at rest, so the simplest k mu for that would be something like it's moving along, let's say, z axis. The light like particle is moving along z axis, so its energy would be some k, and its momentum, space like momentum, would be in the direction z direction, so that would also be k. Now what's the group that leaves this invariant? Well, that is of course the group that rotates the xy plane, so that would be SO 2. That would be our group. But there is another group which is translations in the xy plane. If you translate your space-time coordinates in the xy plane, that would still not change this k, the force momentum. So the rotations, which is a u1, because SO2 is u1, and these translations, they combine to form a group which is called ISO2, or Euclidean group of dimensionality 2. So this is the little group in the massless case. And there are other groups as well. For instance, if you consider m square to be smaller than 0, p naught again greater than 0, that would correspond to a tachyon. That is also technically a mathematical solution, but physically we don't care about it that much. Another group can be such that these p naughts flips their sign, so p naught being smaller than 0 here or there. Another all combinations can be made. All of them are also unphysical. P naught being smaller than 0 would mean some sort of time reversal or something like that. So yeah, that would not be orthochronous. And another class is the one which is such that p mu this is technically a class that your p mu is identically 0. Your components itself are 0, and in that case the only standard momentum you can choose, k mu, is 0 0 0 0, and the whole Lorentz group SO3, 1 leaves that invariant. So that's technically another class. So there are total 6 classes. From these 6 classes, these are the 2 that I described are the ones that we care about. One is the SO3, the little group is SO3, and the other one is ISO2. Alright, so let me just quickly revise the whole thing once. What we said was that the Hilbert space, so first we chose the eigenkets of p mu operator, which we called p comma sigma, as our basis of the Hilbert space. Hilbert space was viewed as a sum of 2 parts, uncountably infinite dimensional Hilbert space of the momentum operator, and along with that we had some other degrees of freedom which we assume to be finite, sigma degrees of freedom. Along with that we had the sigma part of the Hilbert space. Doing a Lorentz transformation on this guy corresponds to on this momentum part. What we are doing is sending the form momentum p to lambda p. So the eigenkets on the momentum sector would be of this form, and this u unitary, which is acting on the whole Hilbert space, would in general would rotate the sigma coordinate as well. So we'll have some linear combination on the sigma sector, which we are representing by this guy, the d sigma prime, which is a function of w, which is itself is a function of lambdas and p's, and there are some constants here which we will fix later on. So this is how the Lorentz transformation act, the unitaries act on the the states of the fixed momenta. This is how they do it, and these d are representations of the little group. Finite, these are finite dimensional, and these are also unitary in such a way. And the little group is defined as this. This group itself is a function of the Lorentz transformation that we are talking about, and the momentum at which we are shooting, followed by lambda of p. And the little group is defined in such a way that any standard momentum k, when this w is acted upon them, we just get back k itself. For the standard momentum for massive case, where p naught is greater than 0 and m square is greater than 0, for that case we choose the standard momentum to be m0 0 0, and for that this corresponds to a particle at rest, and for that any three-dimensional rotation would constitute the little group, because that will not change the standard k mu. And similarly for the massless light-like particles, where m square is 0 and again p naught is greater than 0, for that we can choose a particle, light-like particle, moving along the z-axis. For these, if you rotate the xy plane, that would again be a little group. It will not change the standard momentum k. So that group is ISO2. SO2 is the rotations in xy plane. I stands for two translations that are also possible in the xy plane without tilting the z-axis. So these are the two cases. Our goal would be to use these k mu's, figure out the little group. We know what the little group is. We want to figure out how these things are going to transform. So yeah, that's it for now. And yeah, I think that's all.